In this video, we're going to look at more or additional analytic methods for nonlinear first-order differential equations. And when I made the notes, obviously, I must have done a copy and paste of the first two learning outcomes because they're exactly from the last one. But what we are going to be doing is determining if a first-order differential equation has an exact solution. And then we're going to determine the exact solutions, if it does, of the first-order differential equation. So just a couple of edits there, and then it matches what we're going to be doing. We're going to start with a warm-up where we're asked to find the partial derivative with respect to x and with respect to y, given this function omega in terms of x and y. So the partial derivative of omega with respect to x, which is the same thing as omega with the partial derivative. Notationally, this is the same, just a nice little refresher here. So I'm going to have the derivative of y squared, which is 0, because it is a variable that is not x. So if it's not a variable that's not x, or multiplied by x, then we treat it as a constant. And then we're going to end up with 2xy. As I distribute the y through, I'd have 2x squared plus y, and then the derivative of that would be 2xy, and then minus 6x. So that is the partial derivative with respect to x, and the partial derivative with respect to y, or omega y of xy. And in this case, we'll end up becoming 2y, and then the derivative of y multiplied by that coefficient. We think of x squared plus 1 as a coefficient. Is just going to be the x squared plus 1. And then the derivative of 3x squared, because that's considered a constant, is going to be just 0. So let's explain what an exact differential equation is. So let f be a differential equation of two independent variables, x and y. Then the derivative of f is going to be the derivative of f with the partial derivative of f with respect to x dx, and the partial derivative of the function f with respect to y dy. And we call this the total differential of the function f. Now we know when the df is equal to 0, then the function xy is a constant in some region of the xy plane. Now suppose we are given that g is a function of x and y dx, and h is a function of x and y dy, and it equals 0, then there exists a differential function f of xy such that the partial derivative of f with respect to x is going to be gxy, and the partial derivative of f with respect to y must be h of xy. Then my function xy is equal to c. Generally, this is not the case, and this also makes some large assumptions. So suppose we have this differential equation, which is 2xy minus 9x squared plus 2y plus x squared plus 1 dy dx is equal to 0. Now we know from our calculus 3 in the warm-up that we just did that this partial derivative of the function we just did, omega, with respect to x, is going to be the partial derivative with respect to x of xy dx plus the partial derivative with respect to y of xy dy, which gives us the partial derivative with respect to x, xy, plus the partial derivative of y, xy dy. Now, let's just move the screen up a little bit. So where we are is that we have the dx of omega is equal to the partial derivative with respect to x, which was this, 2xy, minus 9y squared plus the 2y plus x squared plus 1 dy dx. And this actually should be 6 right here. That should be a 6. Since dx of the constant is equal to 0, then the solution of y squared plus x squared plus 1y minus 3x squared plus c. Clearly, we're not going to be given the function to begin with. So why did we just go through this? Well, how do we find these? We're going to have our first definition here, a first-order differential equation y prime as a function of xy is called exact if I can write it in that form. I have some function of, I'm going to call it m, of xy dx, plus some function of n of xy dy is equal to 0, so it's homogeneous, equal to 0. Then the m of xy plus the n of xy dy dx must equal to 0, where m is the partial derivative with respect to x, n is a partial derivative with respect to y for some differential equation. Now in calculus in multivariables, we know that f is twice continuously a differential function in two variables. If this is true, then the second derivative, the second order mixed partial derivatives must be equal. Now I know we haven't got there yet in our Calc 4 class, but it is going to be happening here shortly. So I ruined it for you by telling you this is true. So then m must be equal to the partial derivative of f with respect to x, which means if I take its derivative of m with respect to y, we have the partial derivative of this partial derivative with respect to x first, then y, and then we do the same thing with n, then this has to work out. So in other words, the partial derivative of m with respect to y must be the partial derivative of n with respect to x. So now we have a tool to determine whether or not these equations are going to be exact. And if they are, we're going to give you tools to be able to find the solutions to these differential equations. So let's go ahead and scroll this up and then determine. Now remember, when I have the dx here, this dx, this in front of the dx, this function in front of the dx, must be the m. So my m of x comma y, must be the x plus y. That means my n of x comma y must be this function of x. Now we just take this derivative with respect to x and with respect to y. So I'm going to do a partial derivative of m with respect to y, and I get 1. I'm going to do the partial derivative of n with respect to x, and I get 1. These are equal, so these are exact. Same thing here. M is equal to the sine of y. N is equal to x, the cosine of x. So I'm going to do the partial derivative of m with respect to y. This is going to give me the cosine of x. Now I'm going to do the partial derivative of n with respect to x. And you can see there's a multiplication here, so I have to use the product rule. So the derivative of x is 1, so that's just going to be the cosine of x. And then the derivative of cosine, so that's going to be x multiplied by the negative sine of x. Now these are not equal, so this one is not exact. Again, I have my m is equal to 2xy, my n is equal to x to the third y plus y to the third. My partial of m with respect to y is going to be 2x, and my partial of n with respect to x is going to be 3x squared. These are not equal, so this is also no. It's a nice little check. If it is yes, if the partials are equivalent like it is in A, then what I do is I say, okay, the partial derivative of f with respect to x must be equal to m xy. So then f of xy must be m, the integration of m xy dx plus some q of y. Now, q of y represents the constant of integration with respect to x. So it can also be just c, but it also could be a function of q, or function of y, because we know the derivative of any function and only y, when I'm doing the derivative with respect to x, will become 0. Now we differentiate the function that we found in the previous step with respect to y, and we set it equal to n. We know that this derivative must be equal to this, which means that must be equal to n of y. And if you've done your steps 1, 2, and 3 correctly, the equation resulting from step 3 will define what q of y is as a function of y only. The antiderivative of q of y, we're going to find the antiderivative of q of y to find the q prime of y to find q of y. And the function from step 2 with this value of q of x will provide us the implicit solution. And then we can find the exact differential equation. So let's find the solutions given the initial value problem. IVP is initial value problem. So the first thing we're going to want to do is we are going to want to write this equation, set it equal to 0. So I'm going to rewrite this as 2xy squared plus 4 minus 2, 3 minus x squared y prime is equal to 0. So that is the first thing I'm going to do. Now, you don't have to do this, but I'm just going to do this just because I don't like to have a negative 2. I'm just going to pull that negative through. So I'm going to rewrite this as 2xy squared plus 4 plus 2 x squared y and then minus 3 y prime is equal to 0. So I believe that my m is going to be the 2x squared or 2xy squared plus 4. Now the reason that I do that is because the next term, which is going to be n, is the one that the entire term is attached to the y prime. So this n must be 2x squared y minus 6. I'm going to do my partial derivative of m with respect to y. This gives me 4xy. Do my partial derivative of n with respect to x, which is also giving me 4xy. So these are equal. So because these are equal, that means that we have an exact so that I can move forward and say, okay, I'm going to call this function, call it whatever you want. I'm going to call it big F. So big F of xy will be equal to the integration of my m, which is 2xy squared plus 4 dx plus some function in terms of, I'll call it g, of y. So I'm going to go ahead and integrate this with respect to x, and I'm going to have x squared y squared plus 4x plus g of y. Now, if I take the derivative of this with respect to y, then this must be equal to 2x squared y plus g prime of y, and this must be equal to n. If that's equal to n, then 2x squared y plus g prime of y must be equal to 2x squared y minus 6. That means g prime of y must be equal to negative 6. So then my function that I have, my function of x comma y, must be equal to x squared multiplied by y squared, x squared multiplied by y squared, minus or plus 4x. If g prime of y is equal to negative 6, that tells me that g of y must be equal to 6y, or negative 6y, so I have minus 6y. So now I know from up above that f of xy must be equal to c. So now we're going to find our constant of integration. So we use the initial value. Now our initial value, we're going to do f of, our initial value for this problem was negative 1, 8. So f of negative 1 comma 8 is equal to negative 1 squared, 8 squared, plus 4 multiplied by negative 1 minus 6 multiplied by 8. And I end up, and this equals c, and I end up with c being 12. So what my equation now is x squared y squared minus 6y plus 4x minus 12 is equal to 0. So there is my function. Now, if we look at the fact that it's asking for y of negative 1 is equal to 8, that would lead us to believe that what we're really asked to do is to solve for y explicitly. Now, I'm totally fine if it's not an explicit to leave the answer like this. But to explicitly solve this for y, what we have to do is we have to use the quadratic equation. And what I mean by that is we're going to consider my a being x squared. We're going to consider my b being negative 6. And I'm going to consider my c being the 4x minus 12. So solving this with the quadratic equation, y of x is going to equal to negative b, which is 6, plus or minus the square root. B squared is negative 6, the quantity squared, minus 4 times my a, which is x squared, times my c, which is 4x minus 12, all over my 2 times a, so 2 times x squared. Now you're like, how am I ever going to know this? Well, this is why we're going over it now. We have to decide whether or not we take the positive or negative. Now we know when we put in a negative number, a positive number would come out. So if I were to put in a negative 1 for this, and the only way that I'm going to get a positive number, because this is going to be a number larger than 6, the only way I'm going to get a positive number out is if I take a positive on this plus and minus. So this will be plus, and there is my solution, explicitly solved for y. All right, now we're going to do the next example. You notice how these are involved. They are very involved. And the first thing I'm going to do is make sure that when I do my partial derivatives, that they're going to be equal so that this is explicit. So I'm going to choose m to be all of these terms because they're not attached to the y prime. And so my m is going to be 2ty, well, my variable now is independent variable is t, not x, over t squared plus 1 minus 2t. My partial derivative with respect to y is going to give me 2t over t squared plus 1. My n must be equal to, and I am going to pull the negative through. I'm going to pull this negative through n, and so my n is going to be the positive natural log of t squared plus 1, and then minus 2. That means my partial derivative of n with respect to t, not x, with respect to t, is going to be equal to 2t over t squared plus 1. These are equal, so we know that they're exact. So my f of xy must be equal to the integration of, I'm going to integrate again with the first one. I could integrate the second one, but I'm going to integrate the first one, which is the 2ty divided by t squared plus 1 minus 2t dt plus, now remember we have this should be some function of y, we'll call it h of y. Actually, I think I used g before, so I'll use g again, so g of y. So I'm going to do this integration, and you can see when I integrate the first term, this will become the natural log of t squared plus 1. Now, the natural log, I should put the absolute values, but it is t squared, so that's going to be positive, so I don't have to worry about the absolute value. Oh, and I should have y, because I'm doing the integration, not with respect to t. Well, yeah, because I have the 2t, y, and the y is just a constant, so I have y, the natural log, so don't forget that. And then minus t squared plus g of y. Now we know our next step after we integrate this, which seems counterintuitive, is now we take this derivative with respect to y. This derivative with respect to y, the natural log of t squared plus 1 is a constant. The derivative of t squared is 0. And then I'm going to get plus g prime of y. And we know this must be equal to n. Now, if we look about what was n, that tells me, if I take a look at this n, this g prime of y must be 2, because we know that the natural log of t squared plus 1 of g plus g prime of y must be equal to the natural log of t squared plus 1 minus 2. That means g prime of y must equal -2. That means y, when I integrate it, must, or g of y, when I integrate it, must be equal to -2y. All right, so let me just erase this so I can have the space to continue. Give me just a moment to erase. So we have found the function, and we set it equal to c now. So we found our function. Here's our function right here. So I'm going to just rewrite it over here. So our function, not that one, excuse me, this previous one, bam. So we know our function f of xy is going to be equal to y, the natural log of t squared plus 1, minus t squared minus 2y, and we set this thing equal to c, and we're also going to evaluate it at our initial condition. Our initial condition is x is 5 and y is, not x. God, I keep wanting to put x there. When t is 5, so let me erase this. When t is 5, this is t, this is t. When t is 5, y will be 0. So I have 0 minus 5 squared minus 2 multiplied by 0 must be equal to c. So my constant must be equal to -25. So then what we have is y, the natural log, t squared plus 1 minus t squared minus 2y is equal to a -25. I'm going to solve for y, and this term have y's as multipliers, so I'll bring those together, and anything without a y multiplier will move to the other side. So I'm going to factor out a y, the natural log of t squared plus 1 minus 2 is equal to t squared minus 25. Divide on both sides by the natural log of t squared plus 1 divided minus 2. I'm going to get y as a function of t as t squared minus 25 over the natural log of t squared plus 1 minus 2. And here is my final answer. Now let's take a look at Bernoulli equations. What is a Bernoulli equation? A Bernoulli equation is the form of x prime of t is equal to some function of t multiplied by some function of x plus some function of t, and now x can be raised to an exponent, provided, of course, that exponent is not 0 or 1, and we call these Bernoulli equations. When this is true, then we take and divide the entire equation by x raised to that exponent, and so we end up with x raised to the negative n t x prime of t, p of t x raised to the 1 minus n of t, and then q of t. If we do this substitution, we say let's let v of t equal to x t raised to the n minus 1, then our previous equation becomes p of t v of t plus q of t. Now, we know from calculus that if we take the derivative of v of t, which is x of t raised to the 1 minus n, we're going to get 1 minus n x raised to the n of t x prime of t. Now, if you remember that we just said that x raised to the n, or x raised to the negative n of t of x of t of x prime of t is equal to p of t, v of t, q of t plus q of t, then v prime of t must be equal to this, which is now a nice linear equation. Now let's go through the steps of solving for a Bernoulli differential equation. And to make my notation match, I started out with some y primes and x's and stuff. I'm going to rewrite it so it matches everything else. And I'm going to say, wait, if I have x prime of t is equal to make it match what I had before, p of t multiplied by x of t plus q of t multiplied by x raised to the n of t. Then I'm going to put it in the correct form. I'm going to divide everything by x to the n. I'm going to divide everything by x to the n, which is the same thing as multiplying by x raised to the negative n of t. So it's in the right form. I do this nice substitution. I say let v of t equal x raised to the 1 minus n. V prime of t must then equal that. I use our linear methods that we've learned so far to solve this, and then I back substitute and solve the initial value problem when it's appropriate. So let's go through this example. We're going to solve this initial value problem. And I have y prime plus 4 over x y is equal to x cubed y squared. What I'm going to do is put this in the correct or proper form. And I don't necessarily have to set it for y prime by itself, but what I do need to do is I need to multiply it by everything by y raised to the negative 2. So if I multiply everything by y raised to the negative 2, in other words, divide by y squared, I'm going to get y raised to the negative 2 y prime, and then plus 4 over x. This becomes y raised to the negative 1, and this equals x cubed. Now here's where I would do my u, or in this case v sub. I'm going to let v equal that y raised to the negative 1. And I got that from right here. Now I take the derivative, so v prime is equal to negative y raised to the negative 2 y prime. And if I have negative v prime is equal to y raised to the negative 2 v prime, and I have a replacement for this one, I have a replacement for this one. So this then becomes negative v prime plus 4 over x multiplied by v is equal to x to the third. And that means that if I multiply everything by a negative 1, I have v prime minus 4 over x v is equal to negative x cubed, and this is a linear. So because this is a linear, I'm going to go ahead and treat it as such, and while I'm doing that, I'm going to go ahead and erase that. So I need to find my integrating factor. Remember, we have e raised to the integration of negative 4 over x dx. And this will end up becoming e raised to the negative 4, the natural log of the absolute value of x, which is the same thing as e raised to the natural log of the absolute value of x raised to the negative 4. And then because this is really x raised, or a natural log of 1 over x to the 4th, that's positive, so I don't need the absolute values, so this just becomes x raised to the negative 4. So now I have my integrating factor. Now that I have my integrating factor, I'm going to say, well, v must be equal to 1 over my integrating factor multiplied by my integrating factor multiplied by my g of x, which was x to the third, dx plus c. Don't forget this is all of that. And so I end up with v is equal to x to the 4th. And then inside I have the integration of 1 over x dx plus c. So v is equal to x to the 4th, the natural log of the absolute value of x plus c. So then I have v of x is equal to x, the natural log of the absolute value of x to the 4th, plus x to the 4th times c. Oh, and that should be, damn it, there should be a negative. This would be negative there. So the negative there, because there's a negative there, drop my negative. Don't drop your negative. All right, now we need a back sub. We are going to back sub, and we said, wait a minute, we let v equal x raised to the negative 1. So this v of x must be y raised to the negative 1 must be the negative x to the 4th, the natural log of the absolute value of x, plus x to the 4th times c. And now I'm ready to use my initial value. My initial value from before, so I can figure out what my c was 2 x is 2, y is negative 1. So I have negative 1 raised to the negative 1 is equal to negative, and then 2 raised to the 4th, the natural log of the absolute value of 2, plus c, 2 raised to the 4th. And so I'm going to get c, when I get done solving for c, I'm going to get c is equal to the natural log of 2 minus 1 over 16. So plugging that back in, I have y raised to the negative 1 is negative x to the 4th, the natural log of the absolute value of x, plus, plus the natural log of 2 minus 1 over 16. Now I'm going to solve for y, because it's 1 over y, so this is really 1 over y. So when I solve for y in terms of x only, y of x will be equal to, when I get totally done, negative 16 over x raised to the 4th multiplied by 1 plus 16, the natural log of x divided by 2. And that is what I'm going to get when I am totally and completely finished. And that's my answer. Let's take a look at the second example here. And so first thing we're going to do is get it in the right form. Now this is y raised to the negative 2. So I'm going to, in other words, I'm going to multiply everything by y squared. So I'm going to have y squared y prime is equal to y to the 5 times y to the 3rd plus e raised to the negative 2x. And I'm going to bring 5y to the 3rd to the left-hand side. So I have y squared y prime minus 5y cubed is equal to e raised to the negative 2x. Now I'm going to do with my u sub. I'm going to say let v equal y to the 3rd. That means v prime would equal to 3y squared multiplied by y prime. So that tells me that 1/3 v prime would equal y squared y prime. So here's my replacement here, and I have a replacement here. This then becomes 1/3 v prime minus 5v is equal to e raised to the negative 2x. Multiplying everything by 3, I'm going to have v prime minus 15v is equal to 3e raised to the negative 2x. This is, of course, a linear, just like we did before, in which I find my integrating factor e raised to the negative 15 dx, and I go from there. When I get totally done, I find my initial value, and I'm just going to jump to the answer. Y of x is equal to, ends up being 139e raised to the 15x, and then minus 3e raised to the negative 2x, all over 17, and this thing is raised to the 1/3 when you get done, and that's the final answer. And that's it for this video.